Y'all ready? Let's get this started. Okay, today we start exponential functions. Are there any questions over homework? What's that?
Nothing.
Okay.
Nothing.
All right. I thought today I would begin this concept, this discussion of exponential functions by showing you some visual examples. So if I have this sheet of paper, forget that there's writing on it. I just pulled it out of the recycle bin. How many rectangles do you see here?
One.
You see one rectangle?
Well,
You see two?
There's one, two,
Okay.
three, four, five.
Okay. As basic as we can get here.
Okay, so
This is just two-dimensional. You see one rectangle?
Yeah.
Yeah, we're going basic. I'm going to create a t-table here. This is going to be the number of folds that I put in the paper.
You can only do it 7 times.
This is the number of rectangles.
Unless you go big scale with the
You've seen Mythbusters.
yes, I
Okay. All right. So 0 folds. I haven't folded it. 1 rectangle. If I fold it once in half, and now we count that fold, that crease right there, as splitting our page up. Now, how many rectangles do we see? 2. So 1 fold, 2 rectangles. So let's go back. I'll fold it that one time again. Now I fold it twice. When I open this up, how many rectangles am I going to have? 4. Do y'all agree? All agree? So we get 2, we get 4. And if I fold again, what? I get 8. What do y'all think? 8, 6? 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, you don't see it? 3 folds, 8. What about 4 folds? 16. That's what will happen. We're going to have 4 across the top, 4 down the side, so we have 16. And what's happening every time I fold it? It's doubling, right? So after 5 folds, I should have 32, right? And some of you know that you get to a point where you can't really fold anymore. There's actually an entire Mythbusters, if you've seen that show on Discovery Channel, there was an entire Mythbusters episode dedicated to trying to fold a piece of paper.
7 times, but it was actually, they had to get a paper
It was like
the size of a football field. They got 8, and they had to have a steamroller.
They used a steamroller to try and flatten it out, yeah. I saw one more recently where this guy put a piece of paper in a hydraulic press.
Yeah, they did that too in the
Oh, they did? Okay. It basically like blew up. The whole piece of paper like disintegrated.
Yeah.
So anyway, forget that for a second, because we physically can't fold after a certain point. What would happen if I asked you on this table still, how many rectangles would we have with 9 folds? What would it be? And tell me, if you get an answer, tell me how you're getting it.
So 32, 64. Go down the table. Yeah.
So you're going down the table, right? You're saying,
squares.
because it's doubling, right? It's doubling each time. So you know that 6 would be 64. The next one would be
128.
128, and then 256, and then 512. So this is 1024? Okay?
Well, that sounds good.
That sound good? Well, let me finish the table. 6, I'll do it over here. 6 would have given us 64. 7 would have been 128. 8 would have been 256. 9 would have been 512. Okay, so 9 is 512. 10 would have been 1024. That's not a very efficient way of figuring this out, especially if I asked you, like, you know, if you could fold it 30 times, how many rectangles would you have theoretically? So you would actually, if you're going to follow this method, you would just have to keep doubling each time, right? And go all the way down to 30. There's got to be a better way. So is there a function that takes this as input and spits out the other side? Good guess. Exponential. That's why we're here today, right? But let's see what's going on here.
Well, it's not x squared.
It's not x squared, right? In fact, it's nothing. It's no function that we have dealt with up to this point. It's not linear. It's not a parabola. It's not a polynomial. It's not a rational function. There's only one function that's going to behave like this. It's called an exponential function. The reason they call it exponential has to do with the fact that the power, the exponent, right? The exponent is the power. The exponent is very important in these functions. So what I'd like to show you here is I'm going to rewrite 2 as 2 to the first power. I can rewrite 4 as what? 2 squared, right? 8 is 2 to the third. This is 2 to the fourth. This is 2 to the fifth, and so on and so forth. Do you see that all of them have the same base?
Yeah.
2, 2, 2, 2. The only thing that's changing is the exponent.
So it'd be 2 to the x.
And the exponent is exactly the input, right? So our input is the thing that keeps, our input, our x is the power. And that's what keeps changing. Got it? And does it work for 1?
Yeah.
What's 2 to the 0?
It's 1.
1. So it works there, doesn't it? So this 512 should be 2 to the 9th. So if I wanted to know now 30, I would need to just do 2 to the 30th power. And I would need my calculator, which I asked everyone to bring theirs. 2 to the 30th, try it. So everyone, do we need to have a calculator quiz?
It's 10737418824.
Who wants me to have a quiz grade that you have your calculator here today?
Sure.
I haven't bought it yet.
I told you to bring
I'm
it.
waiting for my paycheck to go
Okay.
buy it.
Well, just get a little $8 one at
Walmart.
Walmart. You don't need a
Oh, I
fancy,
thought we needed a graphing calculator.
scientific,
Oh,
not graphing.
okay.
So it just has to have keys that don't make any sense to you. As long as it has keys that don't make sense, you've got a
Well,
scientific
this
calculator.
thing's got more keys. I don't know what to do with it.
Yeah, then you got, that's scientific. If all it has like plus, minus, division, if it's like, you know, those old school ones. Yeah, go to like Walmart and get a cheapy one.
They do.
Go to Walmart and get a little cheap one or something. Okay? You don't need anything fancy. A lot of people have these fancy calculators, don't know how to work them, so it's not worth having unless you want to learn how to use them.
I think this was.
Okay, so I won't have a quiz today, but if I see anyone without one next time, I'm going to have a quiz. All right? All right.
But you told us last time.
Okay, well, I know y'all have no mercy, my goodness.
Two quiz grades.
Your classmates want me to walk y'all out to the plank here. Okay, I want you to do, I want everyone first to do 2 to the 9th power in their calculator and get 512. And if you don't know how to do it, you raise your hand, I'm going to come by and help you.
Can we use our phones?
You can't.
Calculator?
Not on a test, so in here, no.
As of now, right now. Check it.
No. Yeah.
You want me to read you the numbers?
Did you get 512 though? I'm asking you to do 2 to the 9th first, just to make sure you know what you're doing. Yes?
Yep.
Everyone got it? Okay. 2 to the 30th.
Is 10737.
Wait, 10737.
41824. You might want to put some copies in.
That might help. So this is like a billion?
No. No, it's a trillion.
This is your,
Oh,
you know,
wait,
tens, hundreds, sorry, ones, tens, hundreds, thousands,
No, it's
10,000,
billion,
100.
it's billion.
So,
All right.
we good? About $1 billion or so?
1 billion,
$1 billion. These are pretty big numbers, right? I want you to compare that, okay? I want you to look at the function we had before, like x squared, right? That's a parabola. Plug 30 into this. What's 30 squared? 900? Which one's bigger? I mean, this is like substantially bigger than x squared, isn't it?
Yeah.
And that's the whole idea behind these exponential functions. They grow extremely fast, which is why when you're watching the news, they're like, and the poverty rate is growing exponentially. They love to throw this word around, right? Because it just makes people think like it's growing fast. Do you get that impression when you hear it? They sound like that too? Yeah, I know. Right? Have y'all heard that word before, just by, used by people? It just means, rapid growth. That's the way it's intended to be used. As we're going to see, it doesn't always mean rapid growth. It can also mean rapid decay, meaning that it's going away fast. Okay, what else do I want to talk about with this? What is the actual function? Okay, if we define this function, it would be f of x equals 2 to the x. That's it right there. Do you notice the difference between this and x squared?
Yeah.
Right? The base is 2. The base is actually a number. Your variable is in the exponent. Since the variable is in the exponent, we call them exponential functions. This is not the only exponential function that exists. What if you had f of x equals 3 to the x? That would be an exponential function. You can do 3 to different powers, right? 5 to the x, 10 to the x. But before we look at different varieties of exponential functions, let's talk a little bit about the domain. What you can and cannot plug in for x. So I could plug in 0, right? Could I plug in 1/2? Now look, you have to remove yourself from the folds idea right now, because I can't put half a fold into a piece of paper. Just purely from a standpoint of looking at this as a function, can you take 2 and raise it to the 1/2 power?
Yes.
Because that means square root, doesn't it? And I should be able to do that for all numbers. I want you to do that yourself. I want you to put that into your calculator. I'd like for you to figure out, what would happen if you put 3.5 in here? What would you get? What's 2 to the 3.5? 3137. So look, in this class, this rounding, I'm not going to be real critical on the rounding. We want to go, maybe 2 or 3 decimal places, right? But don't go like 8 or 12 at this point. That's good enough. All right, so it looks like we should be able to plug in, 0 and any number in between, and 1 and 2 and 3, and keep going, right? Haven't looked at negatives though.
Yeah.
What happens? Yeah, so let's talk a little bit about exponents. Do you ever remember seeing this property of exponents? That if you raise something to a negative power, it's the same as doing 1 over it? That negatives drop down? So if I were to ask you to plug in -1 into this, you would actually be doing 2 to the -1, which would be 1/2,
Yeah, that's what I got.
which is 0.5, right? That's what you would get. If you plug in -2, this is 2 to the -2, which would be 1 over 2 squared, which would be 1/4. And what would the next one be if I plug in -3? No, careful. What do we get when we plug in 3? 8, so 1/8, right? So at -3, I should get 1/8. Then I would get 1/16, and so on and so forth, yeah? So it looks like I can plug in all these negative numbers also. So domain-wise, doesn't it look like all real numbers?
Yeah.
Okay. I agree. We're going to graph this. What about the range? What about the things that come out? I think we should look at the graph.
It's not gonna, it can't be 0.
Can't be 0. I agree.
So, but it can be anything above 0.
Above 0, exactly. So let's look. If we plugged in 0, what did we get? I'm graphing it right here.
It acts like the square root, like where it goes like that. Yeah, it's just like the x is root of x.
Square root of x goes like this. Is that what you're saying?
Where's the one that goes like that?
Yeah?
Yeah.
But I don't think it, look, let's just go off our table. If you plug in 0, you get 1, right?
Yeah.
You plug in 1, you get 2. You plug in 2, you get 4, right? And then you plug in 3, and you're going to be off this chart already, right? You plug in 4, and then, I mean, you're just gone, right? This thing goes and grows super, super fast. Yes?
It's kind of like a fraction.
Yeah, so if I plug in -1, what's happening? 1/2, I go up 1/2, right? That's right, it's getting closer to the x-axis. I plug in -2, I get 1/4, then 1/8, then 1/16.
Kind of like the horizon thing.
Asymptote, yes. This is actually a horizontal asymptote. This is what rational functions did, right? Sometimes we had a horizontal asymptote. Same thing. This right here is a rough sketch of the function 2 to the x. Domain, you just said was what? All real numbers. You can say that a couple of ways. I'm going to put -infinity to infinity. And what about the range of this? 0 to infinity. Do I include 0 or not?
No.
No, because I'm not actually ever touching 0 here. As soon as you go above 0, I've got something, right? Any questions on that? This is important. The reason it's important is because what's coming after exponential functions are logarithmic functions. Logarithmic functions are the inverses of exponential functions. And at the end of last class, I told you that when you have an inverse function, the domain and ranges switch places. Do you all remember that? Maybe not, but that's why it's important for us to look at this now. All right, I wanted to show you a bunch of other exponential functions, but while we're talking about this 2 to the x, I think there's a couple of things that I like about 2 to the x that I think are interesting, and, well, now's the time. I may as well talk about it. I want to list out these numbers that I just erased. I want to list them out for you again. We had 1, 2, 4, 8, 16, 32, 64, 128, 26, 256, 512, 10, 24. I keep going, right? Anybody recognize those numbers?
They're doubles of each other.
Yes, but I mean, have you seen them anywhere else in your life? Memory? Memory like oh, like your phone, or like a computer has gigabytes or something.
We start off with 16 and 32.
Right? How many of you own an iPhone? Get the hell out of here. No, I'm just kidding. I'm kidding. I'm kidding. How much memory do you have on your iPhone? What's
16 gigs.
I bet you no one in here has a 30 gig Apple iPhone, right? It's either going to be, well, no one's going to have a 30 though. They're going to have a 32. They're not going to have a 30 though.
Oh,
Actually, with the software.
With the software.
Well, no, I'm saying, yeah, but there's a lot of crap that's in there.
Well, yeah.
Yes, but there's always these increments, right? They're always using these increments.
It's always double.
Yeah, why is it that they always use those increments? I mean, why not make an iPhone that has 20 gig instead of 16 and 32? Do y'all know why?
Because it's the amount of space that they're able to manufacture in the same amount of space.
It's exactly right, because what does a computer work in? What does a computer know? Ones and zeros, right? When you're looking at the internal workings of a computer, it's off or on. That's it. That's all a computer knows. Signal's there, no signal's there. And there's only two states. Everything is a 0 or a 1. That's it. All your fancy little Snapchat videos and all that crap that you do on your phone, whatever it is, it's all a bunch of 0s and 1s. That's all it is. And because of that, hold on a second. I shouldn't have been talking bad about, I think my phone just failed on me. If all you have is 0s and 1s, that's called binary, okay? Two things, 0s and 1s. And since it's two things, everything is going to be in powers of 2.
Although they said that the rate that, because we've gotten basically till the next technology, we're actually starting to get not double.
Oh, no, yeah, I'm not saying that we have to double each time. What I'm saying is that
But
everything's going to be based on a base 2 number system.
But the last 4 years has been very true on how much we're able to get on a signature.
Yeah, I know. We're talking about two different things, though. I'm trying to say that everything fundamentally in a computer is base 2. And if it's base 2, it's 2 to the x. Everything is in powers of 2. All right? You've heard 8-bit machine, 16-bit machine, 32-bit machine, 64-bit machine. It's all because 2 to some power, 2 to some power. What you're talking about is how fast are we actually moving from one, like the first phone you ever had probably didn't have 1 gig, even one, well, first phone I had, shit.
Hey, those
I had a pager, shit.
They were
So,
literally car phones. They came in the car.
yeah. Yeah, I mean, the floppy drives, there's all sorts of things. It's crazy what you can, the comparison. What you're talking about is how fast we're moving up in that space. I'm talking about just the basic language itself is base 2. So that's where those numbers come from, base 2. Here's another, so this is a completely different topic, but it also has to do with what I'm referring to here. Are you all familiar with the March Madness NCAA men's basketball tournament going on right now? Anybody have no idea what I'm talking about? It's okay if you don't.
I haven't been following it as much.
I mean, I'm not asking if you, okay. So the basic idea of this tournament that happens once a year is that there's 64 teams. I know that there's actually more, but let's say 64 teams, and they all play a game. The winners of that game go on to the next round. The winners of that game go on to the next round, and they break it down till you get to the final 2 teams, and they play for the championship, and there's your winner. And at the beginning of the tournament, before it starts, you get on ESPN.com or something, and they're like, fill out your bracket. And they say, try and predict who's going to win. And what they're trying to do is see if anyone can fill out the bracket correctly, right?
Which the chances of that are actually
Which nobody has ever done. Okay, millions of dollars. I think last year, Warren Buffett was offering $1 billion for someone.
for real though. You
So
actually have
let's
better
talk
chances.
about this. All right, let's talk about this. If I have one game, how many different outcomes could there be? If I only have one game, how many different outcomes?
It depends.
Two outcomes, right?
Depends on the game.
No. Basketball.
Oh, okay. 2.
We're still talking about basketball. Okay. So if I have a basketball game, the outcome is one of 2 things, right? So each game, there's 2 possibilities. So for 2 games, right, if I have game 1, and game 2, if there are 2 possibilities here and 2 possibilities here, how many possibilities are there for these 2 games total?
4.
4? Right? What if I have a 3rd game? 2 possibilities.
8.
Is there 8 outcomes or 6?
No, still 6. Are these all going simultaneously?
Yes.
So it's 2, 4, 6.
We're debating this.
Oh, yeah, there's.
We're debating this. Because we need to figure out how many different outcomes there could be. Let's.
Well, I guess it could be a tie.
Oh, let me do this. I'll do it this way instead. Game 1, game 2, game 3. All right? Let's say the teams here are going to be A and B. Teams here, C and D. Teams here, E and F. All right. Let's list out the ways that this could happen. We could have A win, right? We could have C win. We could have E win. Agreed?
Right.
Yeah.
We could have A win. We could have D win and E win.
Then A, then D.
Then A, then
D, then F.
Yeah.
how about let's go. There's different ways. D, how about C and F, then A and D and F? Are these all legitimate?
Yeah.
How many do I have so far? 4. But B could win. How about B wins, C wins, E wins? B wins, D wins, E wins. B wins,
So 12.
C wins, F wins. B wins, D, F.
So 8.
8 outcomes. Do y'all see that? So for each game, there's 2 outcomes, but the total possible ways that these 3 games could outcome isn't 2 times 2, isn't 2 plus 2 plus 2. It's 2 times 2 times 2, which is 2 to the 3rd power, which is 8. Understand that? With me?
So let me guess, your bracket's not going so good right now.
No, what I want to show is how many different brackets are possible. So now let's do this. We have 64 teams to start, right? So we have game 1, game 2, game 3, all the way to game, I keep on writing a 6, game 32. Because they're 64 teams, 2 teams per game. So the first round of the NCAA tournament is 32 games. How many different ways can the first round happen?
2 to the 32.
2 to the 32. So round 1 is 2 to the 32. The next round, there are only 32 teams left now, right? So there's 16 games.
So it's going to be 2.
How many ways can that happen?
2 to the
Round 2 is 2 to the 16. And we are multiplying these. The next round, round 3. How many teams are left?
8.
There's actually 16 teams left, so there's 8 games. So 2 to the 8th. Round 4,
4.
there's
4, 8.
2 to the 4th. Round 5,
2 to the
2
2.
to the 2.
And then
And round 6, which is the championship, 2 to the 1. There's only 2 outcomes in the championship game, right? So remember how we do exponents. If you have x to the n times x to the m, it's x to the n plus m. Okay, so take 32 plus 16, which is 48, plus 8, 56, 60 to 60. 2 to the 63. Someone do that on your calculator, and then who's going to tell me?
It's going to be a big number.
It's going to be a real big number. You got something? Wait, 9 what?
9.22 times 10 to the 18.
Times, now does yours say times 2 or e?
No, I got the whole
You got the
number.
e?
Here, I'll see.
Does anybody have,
I got the whole number.
you do? Okay, that's all right. Let's.
I know mine
What-
was circling.
How many of you have an e thing on your calculator? That means the decimal point needs to be moved 18 places to the right. So it's 9, the point, and then 2, 2, and then the rest of it, let's just say they're zeros. We could get more, you have a bunch, don't worry about it. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's my decimal point. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, approximately this many different outcomes. This many different brackets. That's a cajillion zillion, whatever.
Oh, let's see. That's
Let's see.
million, billion, trillion, something.
Yeah, we start having some weird names that don't match up.
If you ever play that game, Adventure Capitalist, there's like a lot of different.
Okay, so that number is huge, right? That's astronomical. Now look, that's how many different brackets are possible. Okay, if you just start filling out your brackets, that's how many, roughly, how many different brackets are even possible. Now, of course, you don't predict that Duke is going to get beat by UTSA, right? So you can have some, idea of who's going to win at least the first rounds. That's why they call these teams that upset, they call them bracket busters, because they pretty much ruin everyone's brackets. Yes.
If you get really close, do you still get money?
I don't know. I don't think anyone has got past the third round. I think someone had the first 3 rounds correct once. I could be wrong, but I think nobody's got past the first 3. You look it up if you want, if you're interested. So, how many people live on this planet? 7 billion. Let's go 10 billion. Okay, 10 billion. What's 10 billion? It's this. Is that right?
Yeah.
That's 10 billion? So let's take that number up here and divide it by 10 billion. I'm basically going to cancel out, 10 of the zeros? And I'm left with 922000000.
So it's still like 9.
If every person on the planet played and everybody filled out a different bracket, so you're going to go fill out your brackets all different than the ones you fill out, and everyone on the planet does that, we would each need to fill out about 900 million brackets to be guaranteed someone's going to win. Each person has to fill out 900 million brackets differently than every other person on the planet.
You have a better chance of winning the lottery.
You do have a better chance of winning the lottery, probably, than picking this right. But like anything else, you can't win if you don't play. There is a probability, isn't there? I mean, there is a chance it's greater than 0. This is what we talk about when we talk about those asymptotes, something going to 0. It's approaching it without getting there. Chances of you winning this thing are infinitesimally small, but greater than 0.
And people do win stuff like that.
Yeah. Okay. I like to cover that in the spring semester because it's right near Final Four, or right near the tournament, and people, it's there.
He's like, I do it from time to time. It's like you go into his office, it's just like. It's
Yeah,
like
right?
mathematically
I've got like
speaking,
brackets everywhere. I'm sweating all the time trying to fill out brackets. No. No. All right. So let's get back to just the general idea of an exponential function. All right. In general.
But it could be other than anything. It could be something different than 2.
Yeah, 2, I've spent a lot of time on 2, but as we're about to see, an exponential function with what we call base A has the form f of x equals a to the x. All exponential functions look like that in general. It's something to the x power, so your variable's up here. Now, there are some restrictions on a. A can't just be anything. A, the base can't. A, first of all, must be greater than 0. If you take a negative number and raise it to the x, it's no longer an exponential function. In fact, that's something we don't even study. All right, that's a crazy thing, crazy function. It's something we don't study.
Ever?
No, not. I don't think anyone in here, unless you're a math major, would even get into that. Just let it go. You're just going to have to let it go. The problem is that if you raise negative numbers to even powers, you get positive numbers. If you raise it to odd powers, you get negative numbers. And if you try to take square roots and things like that of negative numbers, it's imaginary. That just behaves crazy. So we don't even mess with it here.
Craziness.
Yep. We also have this. We're not going to let a be 1. And the reason we're not going to let a be 1,
Because A is
Yeah, because 1 to any power should just be 1, and that's a pretty boring function, isn't it? So we throw that out of the mix. Other than that, a can be anything. So can a be 10?
Yeah.
Sure. Can a be 1/2?
Yeah.
So we can have nice numbers, 2, 10, 5, but we can also have not nice numbers, 1/2. We could have 1/7. We could have 0.75, anything, except 1 and must be positive. All right. Where did it go?
What are you looking for?
My little towel. Oh, there it is. So I'm going to go and do another example. We're going to take this sheet of paper, and this time we're not going to do folds. We're going to cut it. All right? So I'm going to start off. This is an example. Number of cuts and length. So right now I'm going to say that I measure this and it's 1 unit long, okay, whatever 1 unit is, right? 1 foot. I know it's not. Don't argue with me, please. But let's just say this is like 1 unit. So no cuts, 1. Okay? I'm going to cut this 1 time in half, right down the middle. Perfect, perfect straight line right down the middle. Throw away half. What's the length? Half. Second cut. That's not bad. I've done this many times. I'm doing pretty good up here. Okay, second cut. It's half of a half, right? So a quarter, a fourth. I go again. This is where things usually start going downhill. 1/8, because that's half of a half of a half. Okay.
He's so proud of himself right now.
Years of practice.
He's like,
Yeah.
I finally got it.
Should I go again?
Do it. Do it.
Oh yeah, oh yeah.
Hey, hey.
You gotta stay positive right here. All these people will be dropping out of class.
Shit. All right. But theoretically, you see what's happening here?
I wonder if there'll be a bleep on YouTube.
Isn't this, does this look familiar? Flip all the right sides over, all those fractions.
It's just the opposite.
It's the reciprocal. Let's be careful with inverse now because inverse means something special to us, right? It's the reciprocal, right? This is 1/2. This is 1/2 but squared. This is 1/2 but cubed, right? This is 1/2 to the 4th. And of course this could be 1/2 to the 0, and this is of course 1/2 to the 1. Agreed?
Yeah.
So I could look at this function as being what? 1/2 to the x, as opposed to the problem before where it was 2 to the x. So this would be an exponential function, yes or no? Yes? What's the base of this exponential function? 1/2. As long as that number is bigger than 0 and not 1, which it is, then it's an exponential function. But if I graph this one, it's going to look different than the one we just did, with the exception of one point. What point do they have in common? When I plug in 0, what did I get from the last one? 1. And when I plug in 0 here, I got 1 also, right? So they both go through that point. When I plug in 1, what do I get here? A half. When I plug in 2, I get a quarter, and then I keep going down this way.
But you'll never touch.
But I'll never touch. So I'll have that horizontal. And then the other direction, -1, what do you think is going to happen? So try it out. Try a -1. You can plug in a negative to the exponent. You can't have a negative base. Right? So be careful with that. What happens in that table? So again, we're moving away from the tears. I can't tear -1.
Maybe a 2.
So if I plug in -1, it's 1/2 to the -1. And when you have a fraction to a negative number, you flip. So this becomes 2. And so now on this side with the negatives, I'm going to get all the bigger numbers, right? 8. And so it goes up like this on this side. That should look familiar to you, right? That's 2 to the x reflected over the y-axis. This is our first example of what's called exponential decay. Okay? Because look at it, it's going down, right? Decaying out, going away. As opposed to the other side, which was going up this way. So, you know, we usually read functions like a book from left to right. So if you were reading this, this would be decaying, it'd be going away. 2 to the x grows as you read from left to right. With me? What's the domain of this? All real numbers again. What's the range of this?
It's 0 and then it's positive.
Range. Everything from 0 up, right? So isn't that the identical domain and range from the last problem?
Yeah.
Okay.
But it totally looks different.
Yep. You know, how could we describe what's different about these? We had a technical name for it back when we were talking about properties of graphs.
Reflection.
Yes, that would be a technical name as far as it, but I'm saying in terms of like, yeah, what's it doing? Do you remember if a function goes this like this, we called it increasing? Like, you know, I would ask you like, where is this function increasing? Then I'd ask you, where is this function decreasing? This function, where is it increasing?
In the negative.
Increasing. It's never increasing. Where is this function decreasing? All the time, right? On the other one, 2 to the x, it was opposite. It's always increasing, never decreasing. That would be how we could really describe the difference between these two. All right. So let's talk about the general characteristics of the graphs. That was another specific example. In general, the function f of x equals a to the x looks like one of these. First, if a is greater than 1, not greater than 0, but greater than 1, it's going to look like this. It will always go through the point 0, 1, and it will be exponential growth. So we did 2 to the x, didn't we? 2 to the x, and it was like this. Because the base was 2, 2 is bigger than 1, that's what's going to happen. Now the other thing that could happen is we could have a being, what do you think? Less than 1, but remember a always has to be positive, right? So if I write this, as long as a is between 0 and 1, then it'll be I'll still have that point 0, 1. It'll go up on the left and down on the right, like that. And this is what we call exponential decay.
Exponential decay is always between 0 and 1.
Your base is between 0 and 1. Yes. Uh-huh.
Unless there's like a plus something here.
Unless there's a what? Plus would just move it up and down.
But I meant like you could have like
Yeah.
AZX plus B.
Yeah, and that's where we're going with this. This is what a general exponential function does. Remember when we were learning our toolbox functions, and then we started moving them up, down, left, right, reflecting them, stretching them, doing all that? We're going to do the same thing for this. But we have to have a basic idea of what the basic toolbox exponential function looks like before we start doing anything else to them. All right, we good so far? Graphing. Let's go ahead and list out here domain. We already talked about this. What's the domain for both? Domain, I'm going to do just capital D for domain. All real numbers, negative infinity to infinity. And the range for both, capital R, 0 to infinity. How about horizontal asymptote? I'm going to put HA for horizontal asymptote. 0, right? Y equals 0, because it's a horizontal line. Y equals 0 is a horizontal asymptote. But remember, on the horizontal asymptote, it's only off one end, right? It's only off one end. Look, like this left end goes down to 0, but the right end goes up to infinity. This one, the left end goes up to infinity, the right goes down to 0. So I'm just going to put here one side only. So just be aware of that. Another example here. I want us to do a quick sketch of f of x equals 10 to the x. And let's also do g of x equals 7 to the x.
All on the same graph.
Yeah, let's do them on the same graph because I want us to compare a little bit, like which one's going to be bigger than the other, I guess you could say. Like, how are they going to compare? Are these going to be both growth, both decay, one growth, one decay? What's happening here?
Growth would be growth.
These are both exponential growth. I guess what I'm trying to get at with this example is, which one grows faster?
Well, the one with the 10.
You think the 10, right? The bigger the number should. I agree, yes. But let's just do a quick graph of this. What do they both have in common?
0, 1.
Yeah, they both are going to go through 0, 1. That we know. All right, let's do f. If I plug in 1, what do I get? 10. So I plug in 1, I get 10, which is way up here already. And then when I plug in 2, oh, careful, 100 off the scale, right? So it's going to be like this. And that thing just goes up so quick. Now this way, it's 1/10, then 1/100th. So it drops down really fast, doesn't it? Understand that? If I plug in -1, it's 1/10. If I plug in -2, it's 1 over 100. That's F. Let's look at G. Now I could do a t-table for these, right, and get on my calculator, but when I plug in 0, I'm at 1. When I plug in 1, I'm at 7. When I plug in 2, 49. Not quite as big as the other one, right? So even though these start here at the same place, this one looks like it's going to stay below that one, right? And then on this side, this is interesting. Watch what happens on this side, though. When you plug in -1, what do you get? You get 1/7, not 1/10. Which one is closer to 0? 1/10 or 1/7?
The 10th is closer.
A 10th is closer, right, to 0? So the green one is actually going to be above the red one on this side. And then it goes like that. Y'all see the difference? On the right side, the green one stays below the red. On the left side, the green one stays above the red. But they still do the same thing. They still both head to 0, just the green one is not as fast. They both head up to infinity, it's just the red one is getting there quicker. Now, just for the sake of doing it, you don't need to put this on here. But if we were to graph x squared here, we can see how pathetic x squared looks. X squared starts at 0, at 1 it's at 1, at 2 it's at 4, at 3 it's at 9. So our parabola comes in here and does this business, right? And these guys are already up at 100. The next time they're up at 1,000. And it takes this a long time to get to 1,000, doesn't it? Okay. That doesn't look right. Special?
Yeah, that's right.
It does look special the way I wrote that.
We don't need no vocabulary.
It's okay. It's the math. We don't need to worry about it.
You've seen this number before, right? We talked about pi a little bit, right? We said it's approximately 3.141 something, blah, 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 right? Keeps going, never stops, never repeats itself. We call this, what kind of number? Irrational, right? It was an irrational number. That's not the one we're talking about right now. I just wanted to remind you, okay? There's another number, E. Have y'all ever seen that one before?
Yeah, you told us about it like 3 classes when you were talking about when we would ever use the complex numbers again.
Mm-hmm.
I didn't write
So
it
you've
down.
seen, but I've mentioned E before. E is also an irrational number. It's like pi. It never stops, never repeats itself. So it's irrational, and it's approximately 2.718. And because of that, I could define a function if I wanted to be e to the x. Because 2.718 is bigger than 1, right? I'm sorry, it's bigger than 0 and it's not 1. So I could very well define that, yes?
Yeah, you even showed, I think, e to the pi or something.
Yeah, I was showing you a special relationship. Yeah, I must have gone way off on that day. But this I could do, right? That's a well-defined function. It's an exponential function base e, yes? And if we were to graph this,
It'd be ugly.
we could make a table, and we could start plugging in some numbers like I don't know, 0, 1, 2, 3. But then I need to do what? E to the 0 should be easy. E to the 0's 1. E to the 1 should be about 2.718 e squared. So now get your calculators out. I want you to find your e key. Every scientific calculator has an e key. Do not confuse it with this e.
Yeah,
You should see an E key that's more of like a script handwritten E versus like a capital block E.
Yeah.
We're looking for the one that's more of a script one.
Add e to the x.
E to the x? Yep, see, everyone's calculator is going to be different right now. So everyone try and do, I want everyone to do e to the 0, e to the first, e to the second. Just make sure you can do them all. And if you can't get these answers, let me know.
E to the second is like 7.38.
7.38?
You want the next one?
Nah. Well, yeah, sure, if you have it. E cubed, 20.08. Okay. Good enough.
You got 6?
I mean, it's 5 here.
Yeah, this is good enough. You just want to make sure you're not getting some crazy stuff that doesn't even match. Anyone need help getting those? I'd like for you to do -1 in here. Can I plug -1 in for x?
We're about to find out today.
You can, right? Remember, the domain of the exponential function is all real numbers, so you should be able to plug in
3, 6, 7, 8.
0.3678. Yeah? Plug in -2. We'll just do one more. -2, you get what?
0.135.
135? Good enough.
That's close enough. You could even go -3.
Now, if I were to ask you to graph this, you could actually go and like do a pretty decent graph with these numbers, yes?
Yeah.
But overall, we know that this is going to be exponential growth or decay. What's the base? It's 2.718. If that base is bigger than 1, it's growth. If this base is less than 1, it's decay. So we know right away that this is going to be exponential growth, yeah? But if we wanted to have a more accurate picture, we could actually plug these points in and plot them, couldn't we? Now this function with this base, e, which is a very special number, is one of the most important functions in mathematics. And because it is so important, it's given a name. It's called the natural exponential function. The natural exponential function. And I'll try and explain to you briefly what makes it so important and so special. We were looking for a function, all right? We as in humans. We're trying to find a function that behaved a certain way. We were like, man, I wonder if there's a function that does this, this, and this, because man, if we had that function, that would make our lives a lot easier with some of this math we're trying to do. And we went looking and looking and looking and looking, and finally, we found it. And this is it. And there's no real rhyme or reason to why it is. It just is. It's just naturally occurring. It's just naturally there. Like no one can really explain why it is that 2.718, this weird irrational number, makes that exponential function that we need. Just like no one can really explain why pi is 3.14, not 7.29, right? I mean, like why is pi 3.14? It's just that's the way it is, right? That's the reality of it. And so the reality is that there's only one function that behaves the way we want it to, and this is it. In calculus, you will see what makes it so special. Do you remember, well, I can kind of allude to it a little bit. Do you remember me telling you that in Cal 1, that you do the difference quotient? Remember the difference quotient? And then I said, but there's a shortcut that you get later. It's called taking the derivative, and it's like, okay. This function is the only function that is its own derivative. So if someone asks you to do the difference quotient on that, your answer is that. So what is the difference quotient of, when you set all the difference quotient up and do all the math of e to the x, what's your answer? E to the x. It's the same